As I continue to prepare for my upcoming presentation, if you don't know what it is, I'll be talking about Embalmers clots again. And this topic doesn't go away. And essentially, as I'm pulling all the thoughts together, what I'm trying to figure out is not whether or not they occur, because they certainly do. And I've got here another one of the papers that were done by Bruce Rafley and Matt Sheldon. And they were looking at the proteomic characterization of these anomalous intravascular casts or Embalmers clots. And they were looking at the proteins in it. And so this is part of the presentation that I'll be doing. So just in case you have come along, and sometimes some people are not aware of these things, and they think it's some kind of strange conspiracy. It's like talking about aliens. Let me just tell you, this stuff is real. It's just that it hasn't really been investigated. And the scientists who had been doing this work were doing it very quietly for years. It's just that they are now finally coming forward to say exactly what they have been seeing. And as I had mentioned previously, the whistleblower had sent me this image of a clot that was removed from the inferior vena cava. And these white bits are very strange. This is humongous. This is really big. And this person would only have survived because they took it out. So the person lived. Now, the point is, for me, is not just that they happen. Okay. And embalmers are finding them and have been finding them for years. And the equivalent that I say is that if you imagine hairdressers doing people's hair and, doing the combing and the washing, and they start finding that there are moles in the scalp. And these moles turn out to be, say, a melanoma. Can you imagine the scientific community ignoring hairdressers because they're not scientific? They're not doctors or they're not scientists. They're just making an observation. And this is essentially what the embalmers were doing. They just saw something strange. Haven't really seen this before since 2021. What is it? Why is it there? Why is it happening? Is it relevant? So this is where I'm coming from. And part of my presentation is going to be focused around a very, very important point in that presentation. It's coming up on Thursday. If you haven't yet registered, join me. I'm going to be analyzing these clots, talking about it. And the reason I'm doing it as a presentation is because I've got an insight that was bugging me for a while. And in the paper here, it highlights something that is really, really important. If you look at this here, and this is a preprint, it's not yet peer reviewed. It's the second of their three papers. And they looked at 541 proteins in these unusual clots. And the big red one here is hemoglobin subunit alpha. Second in line is fibrinogen. So these two, this is what bugged me, is that you had hemoglobin here, subunit alpha, and when you compare it to the beta chain here in blue, there's significantly higher amounts of alpha versus beta. Now, the reason that's important is because when you understand how hemoglobin works and what it is and so on, I'm going to show you an image here. This is just a normal clot. And usually in clots, you have red blood cells. And this is why it has that red grape jelly look. But what we're finding is white clots without the red blood cells. So in effect, the hemoglobin inside the red blood cells are being taken out, and then they're being split up into parts, and then the parts are not equal. So this is the bit that was very confusing to me. And what I was trying to work out is that when you look at hemoglobin, this is hemoglobin, there are 270 million clusters of these. And in purple versus red, you have two beta chains and two alpha chains. So they're in equal amounts in the blood. Why in the world would there be more alpha than beta in the clots? And this is what really was bugging me. And I accidentally came across what I think is the answer. And this is what I'll be talking about in the presentation. Because my question, as I said, is not whether or not this occurs, it's what's the relevance clinically. Because the people who have the massive clots, they will either die or they need a procedure to remove it urgently. These ones, you can't miss them because they are so sick. But these clots don't form all the time. And I know this because angiograms are being done every day. That's where we inject dye into blood vessels and they are not seen. So we know that they are not there routinely. And so therefore, my clinical suspicion has been that they accumulate very rapidly. And the question is what could cause such an accumulation of proteins within days to cause a clot that is that big without some unusual mechanism? What would it be that would cause some people, and it's not everyone, and it probably is a small number of people, to be at risk for that? And if it's the case for big clots, is it relevant for smaller clots? Because if people are having smaller clots, they will present with different diseases. They will have clots going to, say, for instance, their kidney or their spleen or a stroke, or blocking an artery to the leg. It's a different presentation because the clots are smaller, or they may have a pulmonary embolus, not a massive clot, so they can make it through. But if these are white clots that they're getting, they don't break up with anticoagulation. And if they don't, we need to know this clinically so that we can figure out ways to mitigate it. Here is one of the insights that I'll be covering in the presentation. When I was doing the research and pulling all the pieces together and trying to identify the specific immune cell, it's a monocyte, THBS monocyte that I'm focused on, I then stumbled into something that I hadn't thought of before. Because the people who are making these clots are breaking them down, breaking down the red blood cells quickly, and also removing the beta chains. And I just couldn't think of what is the characteristic, what are the mechanisms that would cause that to happen. And then this is what I stumbled into. Glucose 6-phosphate dehydrogenase deficiency, G6PD. Now, you may not have heard about this, but across the world, there are over 400 million people who have it, mainly in African and Middle Eastern countries, okay? And the problem with it is that when their body is put under stress, their red blood cells break down. And sometimes a trigger can be just some things like fava beans, and some hydroxychloroquine can sometimes trigger it. And they therefore break down their red blood cells, releasing the alpha and beta chains. And they tend to be more susceptible to inflammatory triggers, which could lead to greater thrombosis and clot formation. Now, if I am right, and this is just my hypothesis, if I am right on this point, what it means is that we could potentially identify the cohorts at highest risk for these unusual thrombotic mechanisms. Now, you may be thinking of the big Embalmers clots, and yeah, those get the most attention when we think about it. But in reality, those big clots, I'm going to show you, like for instance, the extreme end of the spectrum here. This is an example from Richard Hirschman. This is a 19-inch clot that he pulled out of a cadaver doing embalming. And you can see it's white all the way through. But this is at the far end of the spectrum. If the clot is just at the top here, it can still do damage. It's just it presents in a different way. This patient with this clot died, which you're not surprised about. But a smaller clot may not necessarily lead to death. And so the question then becomes, if this kind of clot is forming that is smaller and it is not easily amenable to normal anticoagulation, what do we do? That's a clinical question. And this is why it is not in anyone's interest for the medical and the scientific community to ignore this. Because if you ignore it and it is happening, so just for a moment, if any clinicians are watching this and they are thinking, come on, I don't think this is real. Just think about it a moment. If it is happening and you are ignoring it, what are the likely disease presentations that will occur if clots are forming that are very difficult for the body to break down, and additionally won't easily be broken down even with anticoagulation? If you have that problem, the next question is, well, who is at risk? And is there any way to mitigate that risk? And so that's where we need to go when we're looking forward for medicine. And this is one of the reasons why I'm a strong believer in AI. There's too much ideology at the moment in medicine. People just, I don't believe that. Nobody cares what anybody believes. The question is it real? And if it's real, what do you do about it? If there's one thing I've learned with AI is that it is just objective. If you tell it something, it will look at it. It won't say, no, this is not possible. And this is one of the weak points that we're going to have with regards to science, is the damage that ideology will do to science. If you have ideology, you are not doing science. Science is observation. Is it real? Is it happening? If it's happening, why is it happening? What can we do about it? Who is at risk? How can we mitigate it? Those are the questions that are relevant clinically and scientifically. So remember, coming up in another few days, if you want to hear my analysis, trying to pull all of these things together from the remarkable work that has been done by many in our scientific community. Just to remind you, this is their third paper that had been published. And so this is now out there. So anybody who doesn't believe, it's not yet peer reviewed, but it's definitely out there. 3 papers, Bruce Rafley and Matt Sheldon. I think Bruce is doing a book on these clots and these casts as well, so look out for that. But they are not letting it go. They have been working quietly in the background for years, trying to get this to the forefront. So, final point. Whatever you may think, the first point is that this is real. Richard Hirschman pulled it out. And even if you think he made it up with plasticine, no, they've looked at it and it has unusual patterns of proteins in them. We don't know why or how, and we're still trying to figure it out. But they are real. 2, this is what the whistleblower showed. This is an example of one of these clots. This represents the inferior vena cava. Look at the size of this clot. It's no surprise that the patient was very unwell and needed to have an embolectomy. Mixture of red clots with RBCs and white clots were broken red blood cells and ending up with these very strange patterns. We need to understand what it is. We need to understand what we can do about it. And certainly, if there's one thing beyond the pandemic, we have got to get out of the ideology, because science determines or demands us to find answers. Thank you for watching. I look forward to seeing you in the next few days at the presentation.